Hello, my name is Gal. I'm here with Reyad, and today we'll talk about pseudorandom self-reductions for NP-complete problems. This is a joint work with Robere and Assaf Schuster. Our starting point is random self-reduction. We say that language L is randomly self-reducible if the signed-in membership in L can be reduced in polynomial time to the signed-in membership in L for uniformly random instances. As we can see here, we have X, which is a worst case instance, and we can reduce the membership, the signing membership for X in polynomial time to the signing membership of Y1 to YK, which are uniformly random instances. A famous example is the discrete logarithm problem. First, let's define what the discrete logarithm is. Given a cyclic group G and a generator G, the logarithm of X to the base G is an integer K such that G to the power of K equals X. And the discrete logarithm problem is simply to compute the logarithm of X. There is a very simple random self-reduction for this problem. Given an input X, we pick Z uniformly at random from the group, and we set Y to be X times G to the power of Z. It's easy to see that Y is distributed uniformly at the group, and we can recover the logarithm of X from the logarithm of Y. Another example is computing the permanent of a matrix, and it's important to see that both of these examples are assumed not to be NP-complete. So it is a natural question whether there is an NP-complete problem which has random self-reduction. And Feigenbaum and Fortrow proved that unless the polynomial hierarchy collapses at the third level, the answer is negative. There is no non-adaptive random self-reduction for NP-complete problems, where non-adaptive means that future queries cannot depend on earlier queries from the reduction. The idea of the proof is that given some language L in NP that has non-adaptive random self-reduction, we can construct an AM poly protocol for the complement of L. And from this, it follows that if such a language existed, then the polynomial hierarchy would have been collapsed at the third level. And these results were later improved by Bogdanov and Trevisan. One way to relax the requirement of random self-reduction is to require the queries of the reduction to be pseudorandom instead of random, with respect to some complexity class C. We say that the sequence of distributions D is epsilon n pseudorandom with respect to C. It's a classical definition if for all distinguisher in C, the distinguishing advantage is smaller than epsilon. And similarly, a pseudorandom self-reduction is a reduction where the queries are pseudorandom, which means that they are indistinguishable from the uniform distribution. And Hirihara and Santaman showed a pseudorandom self-reduction for the MCSP problem. Now, there are many good reasons to believe that the MCSP problem is not NP-complete, and they suggested that this fact shows further separation of MCSP from NP completeness. And the reduction works as follows. So there's an input X, which is a truth table of some function, and we simply XOR it with the output of this exponentially secure pseudorandom generator. Now, the output of this reduction is pseudorandom by definition, right? If we assume that G of R is the output of exponentially secure pseudorandom generator, then Y, the result of this reduction, is going to be pseudorandom. And the result of this reduction, of this XOR process, the size of the circuit that computes the truth table of the result is roughly the same as the circuit size for X. And essentially, this is why the reduction works. So MCSP is a minimization problem where there exists pseudorandom distribution D on inputs with small values, right? Assuming the existence of exponentially secure PRG, and XORing the input X with value from D roughly keeps the value of X. And overall, this is why we found that the reduction works. And we try to take these principles and try to apply them on some NP-complete language. And we managed to do it. And the first result that we show in this paper is that the max click problem admits a non-adaptive pseudorandom self-reduction, assuming the non-uniform planted click conjecture. And we also show that more generally, for every non-trivial hereditary property pi, the problem of finding the largest subgraph in the property also admits pseudorandom self-reduction under the same hardness assumption, under the non-uniform planted click. So what is the conjecture? First, we have G n half, which is the uniform distribution over graphs with n vertices. And we have the planted click distribution. We just take a random graph and plant a click of size n to the power of epsilon in it. The conjecture is that there is no polynomial size sequence of circuits that can distinguish between a random graph and a random graph with a planted click with advantage of 1 over n to the tau for some tau between 0 and 1. And now Reyad will explain to you about the reduction.
Hi, I'm Reyad. I will be showing the reduction. So can you go to the next slide, please? Yeah. The reduction is given a graph G with n vertices. It does the following. First, it chooses a state S of size n to the power of epsilon, where epsilon is less than epsilon 0 from the conjecture. It fixes the set S. It fixes all the edges in S and randomizes all other edges. So every edge here on the output, if it's in S, it will stay depending on whether it existed in the original graph, and it will be random with probability half if one edge is if one side of the edge is outside of S. Next slide, please. So some properties of this reduction. First, if the graph G has a click of size k, then f of G has a click of size k divided by 2 times n to the power of 1 minus epsilon with high probability. The reason is that on average, the click size will be at least k divided by the n to the power of 1 minus epsilon, because a click of size k and the random set of size n to the power of epsilon will have an intersection of size k divided by n to the power of 1 minus epsilon. And with high probability, it will be at least half of that. Next slide, please. And the second property is that the click size will not increase by a lot. If f of g, the click size of f of g is not larger than the click size of g plus 3 log n with high probability. The reason is that the click size of f of g is bounded by the click size of S and the click size of the complement of S. On S, it's at most the click size of the original graph. And on the complement, it's at most the 3 log n with high probability. On average, it's 2 log n, and with high probability, it's better than 3 log n. Total, it's the original click size plus 3 log n. The third property is pseudorandomness, which we will show now. Next slide. Now, assume that for some input graph G, an adversary could distinguish between the distribution of f of G and a uniformly random graph R. Then consider the graph f of G, XOR G, XOR K, where K is the complete graph. Now, first, f of G XOR G has an independent set in S, and everything else is random by the way we defined F. So if we take f of G XOR G XOR K, it will have a click in S with size n to the power of epsilon, and everything else is random. So this is a graph with a planted click of size n to the power of epsilon. And the graph R XOR G XOR K is just a random graph because R is random and G and K are constant. So in total, the adversary will be able to distinguish between a graph that is uniformly random and a graph with a planted clique of size n to the power of epsilon, contradicting the planted clique conjecture. A similar trick was used in the MCSP case, pretty much the same sort of trick. So we have pseudorandomness. So in total, what we have is a pseudorandom self-reduction that approximates clique up to a factor of n to the power of 1 minus epsilon, which is known to be NP hard. So there is a reduction from clique to the approximation of clique, and we can compose these reductions and get overall a random self-reduction, a pseudo-random self-reduction from clique to itself. Now, why did this reduction work? Which properties of clique did we use? First of all, that it's small on random inputs. It is approximately 2 log n on a random input. This, with a property of localness or stability, means that fixing a small subset of the input was enough to not change the output too much. And because it's very hard to approximate, this relatively large change of n to the power 4 minus epsilon was enough to show a random self-reduction. It was still NP hard. Now, for general hereditary properties, that's pretty much the same reduction works. The reason is that for any infinite non-trivial hereditary property pi, the problem of finding the maximum subgraph still satisfies the 3 properties. It is still smaller random inputs, and it's also NP hard to approximate with the same factor of n to the power 4 minus epsilon. So the exact same proof works for the general case as well. Okay.
טוב, נראה לי שפשוט נפסיק את ההקלטה כאילו פה, לא צריך, יכולים לשאול שאלות. אם לא רוצים, בואו נראה.
לא יכולתי לשלוט, אבל איכשהו באמצע זה עבד.
אני לא יודע מה...